Our next subject is vector subspaces. And basically we start with a vector space and then we look at a subset of it that has the same properties. So let me go ahead and start. I'm going to let V be a vector space. Then we have a subset H of V is a vector subspace. So let me underline that part. More often than not, you'll hear it or simply subspace. That I'll almost always say subspace and almost never say vector subspace. So anyways, if it satisfies all 10 of the axioms of a vector space. So basically it's a subset that's a vector space itself. So let's look at some examples of some subspaces of things that you've already had a little bit of exposure to. So I'll start with an example and consider the vector space R3. Okay, so what I'm going to do is let H be a subset of R3 where H is defined in the following way. Let's say I have possible numbers in the first coordinate but none in the second coordinate, and possibly numbers in the third coordinate. And these x and z, of course, are in the real numbers. So you see all these vectors that H have basically just have a 0 spot in them. So let's go through the properties of a vector space and see if this satisfies all of them. So, well, in fact, let me do this. Prove that H is a subspace of R3. So remember, there's 10 axioms that we need to prove for this. So let's start. First of all, H is not the empty set because the 0 vector is in H. We know the 0 vector will look like this. 0, 0, 0. It's in H because the second coordinate is a 0, and that's the only thing that H cares about, is that the second coordinate is 0. So this is in there, so H is not the empty set. So we have a non-empty, actually that was not number one, that's part of the description for, it starts out, it's a non-empty set. So let's go through the various axioms and see what happens. So to do this, I'm going to let U equal, let's say U1, 0, U2, and I'm going to let V equal, let's say V1, 0, V2, and these items are both, of course, in H. Now I want to prove that their sum is in H. So let's take a look. If I take U plus V, we have U1, 0, U2 plus V1, 0, V2. Now if you remember, we add vectors coordinate-wise. So I'll have a U1 plus a V1 in the first coordinate, 0 plus 0 in the second coordinate, and then finally U2 plus V2 in the third coordinate. But then if you'll notice, I'll have a U1 plus a V1, still a 0, U2 plus a V2. So you can see that the resulting vector I get from adding them still has a 0 in the middle spot. That's all that matters. The other two, the first coordinate and the third coordinate, can be any real numbers they want, and that's okay. These things up here and in the first and the third row are real numbers. So we have closure under addition. Let's try number 2. That's where we have associate. Actually, wait, no. This is the number 2 was the one where we prove that it's commutative. Well, for all these kind of problems, I mean, the real numbers has the property itself that it's commutative. So I can rearrange the items in there, or in the vector. And this breaks up into v1, 0, v2, plus u1, 0, u2. And of course, that equals the vector v plus the vector u. So there is axiom number 2, which is satisfied. For the third axiom, let's pick another vector that's in H, and we'll call it W, and it will have the obvious coordinates. So let's say if I wanted to do U plus V, and I put parentheses around there and add a W, all of these come from H. The U plus V we already did. That's going to be U1 plus V1, 0, U2 plus V2, and then the W, I'll call W1, 0, W2, since all these things are from H. Now let me add them together. U1 plus V1 plus W1. And then 0 plus 0 is still going to be 0. So that part's not a problem. U2 plus V2 plus W2. And the real numbers themselves are associative under addition. So I can rearrange the parentheses to write it as U1 plus, in parentheses, V1 plus W1, still a 0. U2 plus parentheses V2 plus W2. And I can break that up, of course, into U1, 0, U2 plus V1 plus W1, 0, V2 plus W2. And of course that is the vector U plus parentheses V plus W. For number 4, we already talked about this. The 0 vector equals 0, 0, 0. And of course, since there's a 0 on the second spot, this vector is in H. For number 5, negative U, that's where we make each of the components a negative. Well, negative 0 is still 0. And that is in H, because if U1's a real number, negative U1 is still a real number. So that one was easy to do. Let's see what number 6 is. If I take a scalar and multiply it to the vector, then you take the scalar and multiply it to each component. Well, any number times 0 is still 0, so I have CU1, 0, CU2, and this is in H because the first coordinate's any kind of some sort of a real number, third coordinate some sort of real number, but the big thing is that the second coordinate is 0. Let's see what happens when I take C plus D, these are scalars, and multiply it to my vector. So I have C plus D times U1, C plus D times 0, C plus D times U2. Well, the real numbers themselves have distributivity as a property, so I can break up each of these by multiplying the U1 through. 0 times anything is still 0. Then we have CU2 plus DU2. And I can break these up. CU1, 0, CU2, plus DU1, 0, DU2. Of course, you can bring those constants or those scalars out front. So I can have a C times a U1, 0, U2 plus D times U1, 0, U2. And that's CU plus DU. And of course, that shows that it is, that it satisfies that distributive property. We had a second distributive property that went like this. This time it was a scalar times the sum of two vectors. So this time it'll look like C times the vector U1 plus V1, 0, U2 plus V2. When I multiply it through, I get C times U1 plus V1, C times 0, C times U2 plus V2. And once again, I can use the distributive property of the reals to get the following. I get CU1 plus CU2, 0, CU2 plus CV2, and let me fix this. That was a V1 up there. Now I can break this up. CU1, 0, CU2 plus CV1, 0, CV2. Bring the C out front. U1, 0, U2. C times V1, 0, V2. And that is C times the vector V plus C times the vector U, C times the vector V. So there's that distributive property fulfilled. For number 9, the associativity property, where we have a scalar times the product of a scalar and a vector. So C times du1, 0, du2. I already jumped to the 0 here. I didn't put a d times 0 because, well, that's going to be 0. Now I can multiply the C through. Let's get C times du1, 0, C times du2. And once again, we rely on the properties of the real numbers. The real numbers are associative under multiplication. So this is CD times U1, 0, CD times U2. And now I can factor out the CD. U1, 0, U2. And that shows that the associativity property is working. And then finally, the very last one, if I take 1 and multiply it times U, then I'll have 1 times U1, 1 times 0, 1 times U2. Of course, that 1 doesn't do anything in the real numbers. 1 is the multiplicative identity. So I have U1, 0, U2, which is U. So H satisfies all the properties of a vector space, so therefore H is a subspace. So what I'm going to do is put these 3 dots in case you want to help with your notes. There's 3 dots. That means the word therefore. So therefore, H is a subspace of, well, not V, of R3. Now, you could see that to do this every single time is exhausting. This is just tedious as you can believe. What we have next is a theorem that will allow us to check a lot fewer items, because if you look, let me just run through this for a second. If you look back at all the things that we proved here, how many things are necessary to H itself? So let me go back and start again and see what's important to H itself. So one thing here, having the 0 vector in H is crucial. Well, H being non-empty is crucial actually, but to have 0 in there is one of the axioms of a vector space. So with 0 in there, that is necessary to be in H. So it doesn't say 0 is in V simply because it's in H and H is inside of V. But some of the vectors could be in V but not in H. But nonetheless, H has to have the 0 vector, and there it is. All right, let's move on. If you look at this here for number 1, we have U plus V, and that had to be in H. So that doesn't mention anything about the vector space R3. But now let me go to some other ones here where I have U plus V equals V plus W. When I add them together and I switch them like this, I'm using the commutativity of the real numbers R. That's really not important inside, if I'm using the commutativity for the real numbers and that commutativity makes this subset H work, then it's not really a property of H that it worked. It was more a property of the vector space R3. R3 was responsible for all vectors inside of it commuting. So whether it's an H or not doesn't even matter. These happen to be in H, and we know that their sum is in H, but the fact that they commute, that was really a property of R3. The same thing with associativity. The 0 vector, that had to be in H. If the 0 vector didn't have a 0 in that slot in the second component, then I would fail item number 4, and H would not be a vector space without that. So this fact right here is very much relies on it being in H. Now let's look at some other things. The negative of U is also in H, and CU is in H. So these are crucial because all of these mention H specifically. But if you look at the rest of them, none of them actually mention H specifically, because these rules, the the distributive property, is really true for all vectors in V, not just those that happen to be in H. So no matter what this vector was, this was going to work out. Same thing here. No matter what two vectors these are, whether they're in H or in V, you're still going to have it satisfy that distributive property. And on and on. So let me go ahead and describe what I'm talking about. All of those, proving all those axioms is a chore. So this theorem here is meant to make that chore much easier. So with that in mind, let V be a vector space and let H be a subset of V. Then H is a subspace if we only have to check three things. 1, the 0 vector is in H. 2, for U and V in H, their sum has to be in H. So H has to be closed under addition. And then 3, for a real scalar and a vector in H, C times the vector has to be in H. So that's sort of a closure property as well. But we've gone down from 10 to only 3 properties that we have to check. All right, I have chosen to prove this thing. So let's do a proof of this theorem. And let's check some of the things that have to be true. So we need to prove these following items. I don't want to number them, although maybe I should. We want to show that U plus V equals V plus U for U and V in H. So I want to show it satisfies the commutativity property. We want to show it has an associativity property. Let's see, there's going to be 7 since we have to choose. There's 10 things in all, and we have 3 of them. That must leave 7 for us to try to have to figure out. Well, let me see this for a second. For U in H, negative U is in H. That may seem obvious, but I think I'm going to prove it anyway. So D, if I have C times U plus V, so this is the distributive property, equals CU plus CV. And this is where C is in the real numbers, U and V are in H. E, we want to prove the other distributive property. This is where C and D are scalars, and U is in H. F, we have an associativity type property where C times DU equals CD times U. C, D are in the reals. U is in H. And last, we want to show that 1 times U equals U for U in H. All right, so what if we're going to assume that H has these 3 properties? Also, V is a vector space, so we're going to use its vector space capabilities while we're proving this thing. So let's start with A. So actually, before I start with this, let me do this. Let's start with the beginning here. Let me say let U, V, and W all be vectors in H, or elements, right? It's not a vector space yet until I prove these things. So let those things be in H, and C and D be real numbers. So let me step through the process and make sure that they all work. So for part A, U plus V, E does equal V plus U because U and V are in V. That's a property that V has on its own. For part B, U plus V plus W equals U, well, U plus the parentheses now around the V plus W, because U, V, and W are all in the vector space. So the vector space has that property. For part C, we know the following here. -1 times U equals negative U. We know that from a past thing that we proved. Now, does this mean that this is an H? Well, we assume that CU is in H whenever C is in R and U is in H. So that's already assumed to be true. That means, so this implies that -1 U is in H, because -1 can be a C, or a scalar. But we know that the -1 U equals negative U, so that does imply that negative U is in H. So right there is the first time that we had to actually use anything dealing with H to prove one of these things. Let me move on to D. What was D that we have to prove? A distributive property. So here we know this to be true because all of these things, these vectors, are in V. And V has that property. Similarly, we have the other distributivity because U is in V, and V enjoys that particular property. For F, C times du equals CD times U. Why is that true? Because U is in V. Once again, V has that sort of associativity property. And finally, for G, we have 1 times U. Well, that does equal U because U is an element of the vector space. So most of these properties were because V had the properties themselves. So what did we use in the proving of these things? Well, one of the pieces of a vector space I didn't talk about was that the zero vector had to be in there, and I guess perhaps that might have been an H. Well, I don't think the zero vector is one of the properties of a vector space, but closure under addition, we used that in what application? Well, that's necessary for a vector space to be true. So we did not use it in any of these proofs. So this was necessary for H to even be considered a vector space. We had to have that be true. We did make direct use of number 3, though, in the proof when we looked at part G. That was necessary. And when we looked at part C. So part C and G actually made use of 3. Anyways, from now on, then, we only need to check those 3 items. What I would like to do is redo the problem we had before. So we're going to let H equal, this is a set, x0z such that x and z are in R. We want to let H equal that. Prove that H is a subspace of R3. So we need 3 things to prove. First, let's start with, and here begins the proof. For part 1, the zero vector. Well, we talked about that last time, 0, 0, 0. And that, since that second component is a 0, we know that that item is an H. If I have 2 vectors, so if I take U plus V, we saw from the previous example, that's U1 plus V1, 0, U2 plus V2. Since I have a 0 in that component, we know that item is in H. And finally, if I take C times a vector in H, I get CU1. C times 0 is still 0. CU2. And that is once again in H since the second component is 0. So checking these 3 is obviously much faster than checking 10 axioms. An example. The space with just the 0 vector in it is a subspace of any vector space. Now, for some of these examples, I'm not going to go through the effort of proving them. I might just talk my way through them. And this is a perfect example. Obviously, the 0 vector's in here. If I take this vector plus this vector, it's still 0, so it's closed under addition. And if I take c, any constant c times this vector, it's going to be 0, so it's closed under that kind of multiplication. So you can see it satisfies those three properties, and therefore it's a subspace. Another example will prove that p squared is a subspace of p to the n. If you recall, p to the n are all the polynomials whose degree is less than or equal to n. So p squared are all the polynomials whose degree is at most 2. So if I look at the 0 vector, is very simple. The 0 vector, so if I look at 0t, 0 of t can simply be the constant 0. And that is in these polynomials. 0 is included. I don't know if I mentioned it, but 0 does not have a degree associated with it. It's a polynomial, but we do not associate a degree with it because, well, if you think about it, 0 is the same as 0 times t to the 10th power. Does it have a 10th degree? Does it have a 10 as its highest power? Or you can write 0 times t to the 1000. So we don't have a reasonable way of describing it. We just said that p to the n is all the polynomials of degree less than or equal to n with the addition of the 0 vector. I don't know if that was clear, but I'm trying to make that clear now. So 0 is in p to the n no matter what n is. So that's given already. Now if I take and add to them, so if I let's try this, u of t equals, let's do a naught plus a1t plus a2t squared. And then I'll let v of t equal b naught plus b1t plus b2t squared. When I add them together, I'll drop the t just to make this hopefully more elegant, I suppose. You add like terms, so I'll have an a naught plus b naught plus a1 plus b1 t plus a2 plus b2 t squared. And what results here is a polynomial whose degree is less than or equal to 2. Now remember, it could be like if a1 is the negative of b1, it could wipe out that particular t. Or if a2 happens to be the negative of b2, we may get a polynomial whose degree is less than 2. But it remains that no matter what we do with these polynomials, as far as adding and multiplying by a scalar, we'll never get a polynomial whose degree is bigger than 2. And finally, if we do this, that's simply going to multiply c to, if you use the distributive property, each of the components. And even if c is 0, if c is 0, I'm just in case 1, and we already know that that's in P2. I should probably put that. And same thing with this. Now for this one here, if c is 0, it just zeroes everything out. We know it's okay. No matter what, for any other c, I'm going to get a polynomial probably of degree 2 here if a2 was not equal to 0. And so we can see that this item also is in P squared. For my next example, let V be a vector space and let V1 comma V2 up to Vn be vectors in V. And let H equal the span of those vectors. The span, of course, is the set of all linear combinations of these vectors. So if I take, well, I want to prove, before I do anything else, prove that H is a subspace of V. All right, so you'll remember vectors in the H are going to be linear combinations of these vectors. So if you take a look, one vector, let's call it the 0 vector, looks like 0 times V1 plus 0 times V2 plus, continue all the way up, 0 times Vn. And we know that all of these are the zero vectors. But this item is definitely in H, since it is a linear combination of the vectors in there. And you can see that because I have coefficients that are real numbers. Equal, let's do A1 V1 plus A2 V2 plus AN Vn. That's going to be an H. And let me pick another item in there. I don't want to use V for obvious reasons. Let's use UVW. Let's use W. So I'll call that B1 V1 plus B2 V2 plus BN Vn is in H. Now any of these coefficients, these scalars, if you want to call them, can be 0, and as long as it is of this format, we know that they're in H. So when I add them together, as always, I'll add like terms. So this here is where you begin to see the similarity with this thing and the set of polynomials. They really work the same way in a lot of places. If you think of V1 as being the first entry, V2 as being the second entry, Vn as being the third entry, then the A1, A2, and are exactly like the coefficients in a polynomial. Like same thing with these here. But when you see when I add them together, that most definitely is an H, because all of these coefficients are still real numbers. And it is a linear combination of the vectors in H. And then finally, if I do something like C times U, all that... Sorry, the sound cut out, but you can see that if I apply the distributive property, I'm just going to get C times each of the coefficients. And each of those coefficients, or if you want to call them scalars, they're still real numbers. So this linear combination of the V's is at H. So those were the three properties we needed to use to prove that H is a subspace. First example that I want to do to use this theorem goes like this. I suppose let L equal span suppose L is the span of 1, 2. Then L is a subspace of R squared by the previous theorem. I don't have to do anything else. This L, by the way, L is the line y equals 2x. So you can see that because when x is 1, y is 2, it keeps the same direction no matter what. When you multiply it by different real numbers, you either stretch or shrink this thing or reverse its direction, but you keep the direction going from x b1, y b2. So for every one up you go to the right 2. And well, you know how to draw these lines. You've seen them before. Check it out for yourself. If I stretch it by multiplying it by 10, I simply have 10, 20, which is on that line. And since the real numbers that you can use to multiply them by can really be anything, you can stretch this as far as you want and as far off to infinity as you want to. You can multiply it by a huge negative number and get it to go in the reverse direction as far as you want to, essentially forming that line. Try another one. Same deal. This time I'm going to let L equal, oops, I want the span of that, not just the set. So L equals the span of 1 comma m. So that is a subspace of R squared. In fact, it is the line y equals mx. And you'll find out, although I don't prove it here, that the only subspaces of R squared are these lines through the origin like this, y equals mx. But you can see, once you see it's a span of that, you know you're in business. Let me do some more examples to illustrate that extremely useful theorem. H equal AT squared such that A is in the set of real numbers. Then H is a subspace of P, I guess we could say P squared is actually a subspace of P to the n, but it's a subspace of P squared because H is the same as the span of the single vector T squared. So it's automatically a subspace. Let's take a look at some graphical examples. Suppose let H be the first quadrant in R squared. So H, I'll do just a quick shading figure. I think I'm going to pick a different kind of a color here, like so. So the question here is H a subspace of R squared? Now, when you're doing these subspace things, what you want to do is either prove that it's a subspace or find a single counterexample that goes against one of the axioms of being a subspace. So I'm going to show H is not a subspace because all you got to do is consider this vector. Consider, let's say, U equal to, well, 1, 2. So that means if I go over 1 and up 2, let me draw my vector here. There is U right there. Well, the problem with this space is that negative U is not in H, because negative U comes out in this direction over here. That's negative U, and it's not in the set. Let me make my negative U a little better looking. I made it look pretty bad there. Let's see if I can get it to be a little straighter. There's my negative U. You see it jumps out of the space. Negative U is not in H, and therefore H is not a subspace. All right, well, let's try another one. This time, let H be the union of the first and third quadrants. So this time H is a little bit different than before. I figured since the negative of U popped into the third quadrant, if we include it, maybe we have a better shot of this being a subspace. So let's try it once again. Let me draw this line a little bit bigger and put this right about in the middle. And let me once again mark my territory with yellow to indicate these are the regions for H. Now we have to see if it either follows all of the all of the axioms of a vector space, or we got to come up with a counter example that shows it is not. I plan on doing a counter example. I guess what we could do is let us pick 1, 5. That is in the first quadrant. So 1, 5 will probably, there's like a 1, and then 5 may be way up here. And let's see if I can draw a straight line to connect that. There is 1, 5. So let's call that U. There's U. Next, let me do -2, -1. That is in quadrant 3. So I'm going to call this V. So -2, maybe this is around here. -1 is about here. Let me get my dot to end of it, and let me go ahead and, oops, it's not coming out right. So let's see if we can, oh, I didn't mean to take out that yellow stuff. Let's try again. Well, almost. So there is V. I'll put some yellow stuff back. All right, now let's add them together. That's one of the things, one of the axioms is that you have to be able to add them together and it be in the set. So if I do U plus V, well, if I take 1 plus -2, I'll get a -1. 5 plus -1 will be 4. Well, -1, 4 is here. So if I do -1, 4, let's do this right here. Unfortunately, that thing there is U plus V. And you can see from the picture that it's not in the set. So therefore, H is not a subspace. Specifically, it's not closed under addition. Let's see, try this one here. H equals, I'm going to take a subset of R3, I think. So what I have is 2x plus 3y, -5x, 10y, such that, so H is generated by these things. X and Y are in R. So you can see H is a subset of R3. Now, pick an element out of H. Let's let U equal, oh, I don't know, pick some sort of an item from H. 2x plus 3y, -5x, 10y. I'm going to rewrite this a second so that you can see it more clearly. I have 2x plus 3y. Let me make that x better. I have -5x plus 0y. And then I have 0x plus 10y. Well, from this, you can see I can break this up into the following two things. I have 2x, -5x, and a 0, plus 3y, 0, and 10y. Well, let me go one more step. I'm going to factor out an x. And I'm going to then factor out a y. Now hopefully you can see, since x and y are real numbers, this is nothing more than a linear combination of these two vectors. So this item is in the span of those two vectors. So what happened was I picked an item inside of H. U was any arbitrary vector that was inside of H. And so I showed that any item in H was also in the span. So what I've shown is that H is a subset of the span of 2, -5, 0, comma, 3, 0, 10. Now, what I actually want to do is show that H equals that. Then if I can show H is equal to that, I know that this set H will be a subspace because it will be equal to the span of vectors. Well, pick an item out of the span. So let V be in the span of 2, -5, 0, comma, 3, 0, 10. Now recall that that means is that V is going to look like A times 2, -5, 0. Essentially, V is going to be a linear combination of the two vectors. Now let me put it back together. I'm going to multiply the A through. And then let me add it together. 2a plus 3b, -5a, 10b. Well, that's going to be in the set x because your a, it doesn't matter if I call them x or y or a and b. A and b are just real numbers. So this v is also in H. Because let me go back. I sort of lost track of what H was. H are all vectors of this format. So mine, I just had an A there and a B there, an A there and a B there. As long as this letter matches this letter and this letter matches this letter, and of course the coefficients are set up, everything's good. So what I've done is this implies now that the span of, what was it, 2, -5 and 3, 0, 10 is a subset of H. So since H is a subset of the span of those two vectors. Did I get a negative in there somewhere? 2, -5, 0, comma, 3, 0, 10. Since H is a subset of that, and, well, I'll put it this way. This is kind of an interesting way to put it. That thing is a subset of H. Therefore, H equals the span of 2, -5, 0, 3, 0, 10. Another therefore. Therefore, H is a subspace of R3. So let me do one so you can see these quick. Here, this time, I'm going to let H equal I guess I'll stick to R3 for a while. 7x, 5y, and 2, such that x and y are real numbers. Now the problem here is that H is not going to be a subspace because this 2 is going to be problematic. Note that 0, 0, 0 is not in H, because no matter what, everything that's in H has a 2 as the final coordinate. That does not. That, as we know, is the 0 vector in R3. So this implies that H is not a subspace of R3. You might recall, I don't know if we've had it or not before, recall, M, and I put a little M cross N, is the vector space of M by N matrices. And I don't know if you have to step through it in one of the homework problems, but it's not really hard to show that these vectors are. They add together fine, and when you multiply a constant to it or a scalar to it, you simply multiply all the entries by that scalar. So there should be no big deal. Let's take a look at an example. Let me have H equals the following set. I'm going to set it up as A11, A21, A31, 0, 0, A22, 0, A23, A33, where each of the aij's is in R. This set is a subspace. These are all the lower triangular matrices. And, well, they would have to have the three properties here. I can look and see. I'll show you in a minute a second way of doing this. But for the first part, the 0 vector, which is just the matrix of all zeros. Here I'm in M3 by 3. I probably should have picked something a little more exotic, but I didn't. That, of course, is in H, so I've got that. Remember, I got three things I've got to prove. There's one. Second one is if I add them together. So A11, A21, A31, 0, 0, A22, 0, A32, A33, plus, let me have a second one, B11, B21, B31, 0, 0, B22, 0, B32, B33. When I add them together, I get the following matrix. A11 plus B11, that's in the first entry. The second entry is 0 plus 0. You still get a 0. The third entry here in the first row is still 0. I'm giving myself space for all the additions I might be doing. For the second row, we add A21 plus B21. That's the first entry. The next entry, I have A22 plus B22. And then 0 plus 0 is still 0. And then finally, A31 plus B31, A32 plus B32, and then A33 plus B33. So you can see that what I have here is still a lower diagonal matrix, so that item is also in H. And then finally, you can probably see this without much ado. If I take C and I multiply it by a matrix, then you simply multiply C times each of the items in that matrix. And you end up getting CA11. Well, C times these zeros is still going to produce a 0. CA21, CA31, CA22, CA32, 0, CA33. And since it's lower diagonal, that item is also an H. Therefore, H is a subspace of M3 by 3. Sometimes they'll just write M sub 3 when they want you to know that the matrices are all square. In fact, you can play games if you want. Well, I think you should see that nothing that I did here was so extraordinary that you couldn't repeat the process for an upper diagonal matrix. You can repeat the process for a diagonal matrix. You can repeat the process for any set like this with any number of zeros in it. It doesn't have to be upper or lower diagonal. I can have zeros in odd number of places, and they just stay there no matter what I do as far as adding or multiplying by a scalar. Now let me show you something here. I can say, though, that H is spanned by certain vectors. Let me show you. So let me redo this example. This is a redo. So H equals, once again, I'll write it again, A11, A21, A31, 0, 0, A22, A32, 0, A33, such that Aij is in R. Now I'm going to do like I did in the last time, and you can rewrite this. Let me give myself a span. You know, if you can get it to be a collection of vectors and write it as the span of those vectors, you know automatically H is going to be a subspace. So what I'm going to do is this. H is spanned by 1, 0, 0, 0, 0, 0, 0, 0, 0, comma, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. I'm almost done. Let me see. Then I'm going to have 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, comma, and here's my last one, 0, 0, 0, 0, 0, 0, 0, 0, 1. And you can see that if I were to take all of these matrices and simply add them together, you would get a lower diagonal matrix of all ones. But you can see that this is the span of these. If I multiply this one by A11, multiply this one by A21, as constant, I'm talking about A11 as a real number. A11 times this would put an A11 in that spot. A21 times this matrix puts an A21 in this spot. A22 times this matrix puts an A22 here. A31 puts an A31 in that lower corner. A32 times this next matrix puts an A32 down here. And then finally A33 times this matrix puts an A33 down there. Take and add all of those up and you get exactly this matrix. So once you know it's the span of a collection of vectors, then you automatically know that H is a subspace of M3 by 3. And it doesn't matter. You can play with matrices of 5 by 12, 2 by 4, whatever. And have it be any collection. Like I could leave any number of things blank in there or zeros in there and it will work. You can't, now notice I can't leave any of these numbers like a 1, or if these were non-zero numbers, like this was a 5, as soon as I would add it to itself, then it would be a 10 in that spot and it would ruin the chances of it being a subspace. As a last example, look at R2 is not a subspace of R3. Why? Because in R2, vectors look like this. They have 2 rows. And in R3, vectors look like this. So the problem is that you need another row for it to be in R3. So you can see that it's not even a subset. R2 is not even a subset of R3. R to the M is not a subspace of R to the N if M is less than N. For the same reason, you don't have enough rows. So basically Rm will not be a subset of R to the N. We'll talk about things. There's like a copy in this example here. There is a copy of R2, but there's something called an isomorphism, which we haven't spoken of yet. If I were to put a 0 on the third spot, I would have a creature that acts just like R2, but it is actually a subset, and a subspace of R3. But I'll stop there. I think this video's gone long enough.